All right. Well, good afternoon, folks, and hopefully you had a chance to work through the video yesterday, the lesson yesterday, and then I want to continue on with that discussion today of using that second kinematic equation. So at this point, then we've come up with two different kinematic equations that we can use. And again, make sure you understand that what these kinematic equations allow us to do, it allows us to make predictions, just like any other equations. It allows us to make predictions about what will happen if certain variables change. In these particular cases, we've been talking about how we've been describing motion, and so what we can do then with the kinematic equations, so we can predict what will happen with velocity or displacement if we know something about the acceleration, for example. And so that's the idea, the central idea behind solving these kinematic problems, and that is, can we make predictions about how an object moves if some characteristic, some aspect of the motion changes? Okay? And so make sure you understand that the way we're describing motion right now has been very simple. We've been describing it in terms of the direction of the motion, and that we can assign in terms of the sign, the positive or negative, or the direction that we give to the motion, left or right, up or down, south or north, east, west, and so forth. Okay, so we can describe motion in terms of its direction, in terms of how far the object moves. We talked about that as displacement. We can describe the motion in terms of how fast the object moves, and we describe that in terms of velocity. And then finally, how quickly that velocity, that speed changes. And we describe that in terms of acceleration. So really, when we describe motion, we're describing it in four basic ways: direction, velocity, displacement, velocity, and acceleration. Okay, and so with that said, the kinematic equations, if you take a look at it, incorporates three of those four. The direction you have to determine on your own, but the kinematic equations relate acceleration, velocity, acceleration, and displacement. And so we are able then, using the kinematic equations, to describe motion very effectively and predict how an object will move very effectively using simple equations. Using simple equations, and that's the whole idea behind kinematics. Okay? And so what we did then is I derived for you an equation yesterday. We used the velocity time graph. We used the velocity time graph. We described then how an object, we can use the velocity time graph to predict then motion of an object that's moving at constant acceleration, either constant zero acceleration, which means that there is no acceleration and thus the velocity is constant, or constant non-zero acceleration. In that case, then the velocity is constantly changing. And so we said that in real life, objects will do when they move will have a combination of both. It means then they will move with constant non-zero acceleration. That means constant velocity, and then they will constantly change that acceleration as well. Okay, over short intervals of time, that's what we're going to notice. Okay? And so we were able to incorporate in a single kinematic equation an object that moves at constant acceleration, constant non-zero acceleration, with constant zero acceleration. Okay, so that's what we have to do. And so I left off with this particular problem here. And so let's take a look at this problem here. So we have the object here is a man. We have an object, this particular object here. This man runs initially at a constant velocity. So constant velocity, make sure you understand that, understand the clues that are given to you here, folks. Understand the clues that are given to you here, okay? And if you understand these clues, you can do this. So constant velocity here, whenever you see that, that means then acceleration is going to be equal to zero. This is zero, constant zero acceleration, okay? That's what constant velocity means. That means then the velocity will not change, okay? So therefore, in this particular moment, the velocity then is going to be 4.5 meters per second, okay? And that doesn't change. And it doesn't change for this time interval here, which is 15 minutes. So he moves at this rate for that long. Okay, so that's what we know about the first nature of his motion. Okay, so in the one part of his motion, that's how we can describe it. He doesn't accelerate, he moves at a constant pace, okay, and he moves at a constant pace for 15 minutes worth of time. And I'm sorry, the last variable that I failed to forgot to mention to you is that is when we describe motion, we have to also describe within a time interval. Okay, so we have acceleration, displacement, velocity, and also time. Okay? All right. So with that said, then, does the man change the way he moves? Yes, he does. Okay, so he gets to this hill here, and then what do we notice? He slows down, which means then this is acceleration. At this point here, he has constant acceleration that is not zero. The acceleration is constant still because we're saying that it slows down at a constant rate here, okay, and that is the acceleration there. Okay, so they give us the acceleration in the second part. So we call this A1. That's the acceleration in the first part. The acceleration in the second part then is going to be 0.05 meters per second squared. Okay. And since the velocity still is positive, okay, we know that the acceleration here is going to be negative. Okay, the acceleration there is going to be negative, okay, but we don't quite we won't quite use that in this particular case here. So that's what we have there. Okay, but then with that said, then we're told then that he comes to a stop, which means then the final velocity here is going to be 0. Okay, and that the time interval that he takes to come to a stop then is going to be 90 seconds. Okay. All right, so those are all the things that we know about this particular motion here. Okay, so we have then, we're going to take all that information and we're going to use it to solve for this problem. Okay, so what I'm going to do then, let's go ahead then and let me clear this up real quickly. Okay, and so this is essentially the motion. Now, the numbers aren't quite the same, but this is essentially the motion that this runner is undergoing. Okay, the runner initially starts out, has a constant velocity, and I'm going to go ahead and what I would suggest you do, and this is something that I've always suggested, and I'm going to do this here for you now. Okay, draw a simple diagram. Okay, so the runner starts out, it moves in a certain direction. We're going to say then in a positive x direction here. Okay, and then what we're going to say then is that for the first part, okay, we'll describe that as delta x1, that he undergoes a displacement in the first part because the motions are different. How he undergoes that displacement is different as in the second. Okay? And so with that said, then we saw in this first part of his motion, first displacement here, his acceleration was 0. He had no acceleration, which means then his velocity was constant. Okay? So the velocity was constant. And so therefore, the velocity we were told then is 4.5 meters per second. Okay, and he underwent this motion for 15 minutes. So understand this: the runner here is moving in 2 different ways. Okay, and so we're describing it in 2 different ways. Okay, so in this first phase here, he has no acceleration. He moves at a constant velocity. Okay, and therefore then, and the time interval that he does this for 15 minutes. Okay, then at the end of 15 minutes, he changes the way he moves. Okay, and so he undergoes a displacement here in A2, okay, in which he has an acceleration of 0.05 meters per second squared. Okay, and we said then that's negative because he's slowing down. Velocity is positive. Okay, and therefore then if we consider this motion, then at this point here, his initial velocity is 4.5 meters per second. His final velocity, because we're told he comes to a stop, is 0 meters per second. Okay, and he does this for 90 seconds. Okay, and so that's the second part of his motion. Okay, and so we could actually say here that for the first interval here, he has v final or v initial is equal to v final, which is equal to 4.5 meters per second. Okay, all right. So I think so that's how you want to do that. So I think the way that we can draw this graph more accurately, okay, and so this is just the slowed down part here. If we were to draw the velocity time graph here, okay, for the way this runner moves, okay, so this is velocity over time, okay. If we were to draw this graph here, we can imagine then that he moves this way, constant velocity initially, okay, and then he starts to slow down. Okay, so that would be how we would describe this motion. So this represents displacement 1, and this represents displacement 2. And you have to be able to do that as well. Okay, all right, so how would we find the total displacement for this object here? Then we would find then that it would be for the total displacement, we need to find then the displacement for 1 and add that to displacement for 2, which means then we would take the area underneath 1, so that would be the area for the rectangle plus the area for the triangle there, and we would add it together, and that's it. Okay, and remember the area here is going to be velocity and time. Okay, so let's go ahead and plug this in here. Okay, so here we have constant velocity length here versus time, okay, which means then we have then 4.5 meters per second times time interval here, which I'm going to leave blank just for a moment. Okay, plus let's go ahead and deal with the second one here. 1/2. Okay, base times height. Okay, base then is going to be the time interval here of 90 seconds times the height here, which is 4.5 meters per second. Okay. All right, so let's go ahead and let's determine what we have right here. Okay, so the time here is, and I left this blank for a reason. I hope you recognize why, because the time here is in minutes. Okay, and we have a time unit here of seconds. So what do we have to do here? We have to do our conversion. So let's go ahead and let's convert the time unit up here. Okay, so let's go ahead and let's convert this time unit to seconds. So we have 15 minutes. And we want to find the equivalent units in seconds. And so what I would like to do is take a couple of minutes, take a minute, plug that in, and we need and calculate for this value right here. I'm going to stop right here, okay? I'm going to ask you to do this conversion as practice, okay? So plug it in, and then what would your answer be in seconds? Okay, well, how many seconds in 15 minutes? Okay, so take about a minute and get that calculation done. Okay, go ahead and do so. Okay, so hopefully you saw then that the conversion factor we're going to use here then is 60 seconds over 1 minute. We have 60 seconds in a minute. We plug that in. We end up here with 900 seconds. And so, folks, like I was pointing out to you when we were doing these conversions, you will have to be able to continue to do these conversions, and you have to do that in order to make sure that the units cancel out. So you have to do this conversion here. Either you do this first and you see that you have to do so, or you can do it like I did right here. Okay, so therefore the time interval here would be 900 seconds. Okay? All right, so plugging that in then, folks, let's go ahead and do so. Plug that in. That's 4.5 times 900, that's gonna be 4,050 units here cancel out. That's gonna be meters. Okay, plus 1/2 base times height. Let's go ahead and plug that in really quickly. Let me go ahead and punch that in for you. So we have then 90 times 4.5 divided by 2, you get then 202.5. Okay, so 202.5 meters. Okay. All right, so with that said, then you add those together, you get your final answer then, 4,252.5 meters, or rounded to 2 significant figures, it's going to be 4,300 meters. Okay, so we got this answer here, folks, from the graph. Okay, we got this answer here from a basic graph and then finding areas underneath the curve. You can go ahead and do it that way if you want to. You can do it that way if you want to, but then we had a second way. So this is one alternative here. The second way that we can solve for this one, folks, then is using the equation. You had then delta x is going to be equal to bt plus 1/2 at squared. Okay? And you saw how we were able to derive that equation yesterday. So make sure you take a look at it again. But with the equation here, folks, the way it's set up, we can just plug in our values. Okay, so again, let's go ahead and do so. The velocity in the first time interval here, we have it right here. The velocity in the first time interval here is 4.5 meters per second. Okay? And that time interval here is 50 minutes, which is 900 seconds. That doesn't change from what we did right here, okay? But the second part does change, okay? So we have the 1/2. The acceleration here, we're gonna use the absolute value of the acceleration here because we need then the distance traveled, okay? And he doesn't travel in the opposite direction. He still continues to travel in the same direction. So we're gonna plug that in then as absolute value of 0.05 meters per second squared, okay? And the time interval here is gonna be 90 seconds, and we have to square that, okay? All right, so if you plug those values into your calculator and you solve for it, sure enough, what do you get, folks? You're going to end up with 4,252.5 52.5 meters, which rounded to the nearest, to two significant figures would be 4,300 meters. And so I wanted just to show you then that both techniques work. It's just this technique here, this method here is just a little bit faster than here, where you, again, here you have to draw out the simple picture and diagram here, but it'll work. Simple graph here. See then that you have to add these areas together, and you get it done. Both methods will get you the same answer. Okay, so hopefully you can practice that a little bit, and I'll try to post practice for this. And I'm sorry, I'm a little bit behind in that. I'll try to post practices for you on this one here. Okay, and then practice this, and get it done. Okay, I think the more practice you get it, the more practice you do, the better you'll get at it. Okay, so or come by and see me and get help with this. Okay. All right, so very good. So let's go ahead and let's continue on then, because there is a final kinematic equation, and this I will not derive for you. But the derivation for these two equations here, okay, the derivation for these two equations, very straightforward. And actually, they're the same equation. All we did here in the second part is expanded what was in here. Okay, is that you basically combine together. If you combine together the first kinematic equation and the second kinematic equation, and I would challenge you to do this. So let me go ahead and write this down here. Okay, so the first kinematic equation was V final equal to V initial plus a t, and the second kinematic equation is delta x is equal to V t plus 1/2 a t squared. Okay, so combining these two together, okay, and then simplifying. For those of you who are up to the challenge, go ahead and do so. Combining these together and then simplifying to solve for V final, you will be able to solve for, you will be able to obtain this. Keeping in mind then that acceleration, make sure you keep this in mind, acceleration is equal to, this here, that you'll also need to be aware that acceleration is equal to delta V over t as well. Okay, so combining those three equations together, okay, and substituting, you will get these this equation here. So what does this equation give us? It gives us, if we know initial velocity, acceleration, and displacement, we can get final velocity. Okay, so what's missing from this equation? Time. If we don't have any reference to time, we can still solve for displacement. We can still solve for final and initial velocity. We can still solve for acceleration if we know the other components. So that's where this equation comes in really handy, and this is where an equation you can use if you don't have any reference to time. Okay? So let's take a look at an example here of a problem that where we would have to employ this equation. Okay, so let's go ahead and take a look at what we have here. Okay, so we have here a problem in which we are told then that we have an object, an automobile here that starts from rest. So that's going to be important. I'm going to highlight that for you. And then we're told it speeds up at this rate here, and that I'm going to highlight that for you as well. Okay, and then we're told then that we have this rate here. Okay, and the question they're asking you is how far. Okay, so what are we given here so far? Well, rest then, folks, hope you recognize this, is a velocity. So we were given a velocity of 0 meters per second. That's what rest always means. Okay. Here then, we're told then, if you look at the units, it speeds up at this rate here, which means then this is an acceleration. So we're given an acceleration. Okay. And then finally here, we are given a velocity that is a final velocity. Okay. Okay. And so, I'm sorry, start from rest means then that this is the initial velocity. We're told then that this is going to be your final velocity. It speeds up at this rate at 3.5 meters per second squared. So that's the acceleration. This is our initial velocity. This is our final velocity. And here what they're asking us then to do is to find then the displacement. Okay. No reference to time here. We're not told how long this movement, this motion is taking place, but we are asked to find how far. Okay, so that's what we have listed. That's what you have to be able to identify. Okay, so what I would suggest you do, let's go ahead then and let's work this problem out. Okay, I would suggest then you draw a simple picture. Okay, let's start out with a simple picture that we're going to draw here. Okay, and then I would take what you just labeled there and put it into the picture. Okay, so here is our car here. There's our object. Okay, mass m. There's our car. Moves at a certain distance. Okay, so moves for a certain distance here, and we'll mark off this part here as delta x. Okay, And that's what we're solving for, folks. Okay? And so with that said then, I'm sorry, that's what we're solving for. Let me go ahead and take a little bit more of your time. We're running a little low on time here. Okay, let's list again what we have in our picture. Okay, so acceleration then, we're told the acceleration is 3.5 meters per second squared. The initial velocity over here at the start point, okay, is going to be 0 meters per second. At the end point here, V final, we were told then that he is moving, the car is moving at 25 meters per second squared. Okay, and so what we were asked to find then is how far does the car move if this is its acceleration to reach that final velocity. Okay, all right, so let's go ahead then. Let's plug in what we have. Okay, so that's what we're given. The equation that'll give us the final and there is no reference to time. Okay, to give us that displacement then, it's going to be V final squared. It's going to be equal to V initial squared plus 2A delta X. Okay, so here's what we have here, folks. We don't have any time, but we can solve for delta X here. That's our displacement if we have acceleration. Do we have acceleration? Yes, we do. It's given to us right here. We can solve for delta X here if we also know the initial velocity. Do we have initial velocity? Yes, we do. It's right here. Okay, and then finally, we can solve for delta X if we have the initial final velocity. And do we have that? Also, yes. Okay, so we have everything we need to solve for displacement except the appropriate equation. Okay, so here's what we start out with. We would have to rearrange this equation here in order to find delta X. Okay, so to find delta X then, isolate delta X all by itself. Hopefully you recognize here then, first and foremost, we would have to subtract V initial from both sides. Okay, so it's going to be V initial squared. We subtract from both sides, and then we would divide both sides by 2A. And so there it is. Okay, there is our equation to solve for delta X. Okay. At this point then, folks, it's plug and chug. Let's plug in our numbers and see what we have here. V final is given to us here as 25 meters per second. Okay, so that's squared. So don't forget to square that. Okay, minus V initial, which is 0 meters per second, and that is also squared, all over 2 times the acceleration, which is 3.5 meters per second squared. Okay, all right. So you plug those numbers into your calculator, and you will get your answer then as being 89 meters. All the units will cancel out, 2 significant figures, and that is your final displacement. Okay. All right. So what I would like to do then is let's go ahead and make sure you write this down. Okay. And what I'd like you to do then, just to finish up here, I want you to start this problem here. I want you to start this problem. If you can't solve for it, that's okay. But I want you to at least draw the picture, label your picture with the information here, and try your best to solve it for it, and then have this with you tomorrow. And I'm going to use this, we'll start with this problem tomorrow, and you can compare your answer to what we came up with, what we'll come up with tomorrow. Okay, so work this problem out, use the rest of the period to work this problem out, okay, and then have it for tomorrow. Okay, make sure you submit your work. I'd like to see what you do. Okay, make sure you submit your work, and then tomorrow we'll go over this problem. Okay, all right, folks, very good. Have a good day, and I will see you tomorrow.